All right, good morning or good evening, class. We're looking at lab number 6 for the lab, which is series parallel combination circuits. Series parallel combination circuits. So this is what you would start with if you go to modules. You can go on the module number 6. You're going to see the lab. Again, it's series parallel combination circuits. So you will click on this link to get access to the lab. I have it open already, so I'm just going to roll from there. I want to take you through some of the introduction. I have a video already recorded with the experiment. So again, this lab, this set of objectives, you want to be able to measure the equivalent resistance for a series parallel combination circuit, and also you want to be able to compute or perform analysis to find all of those results as well. So in this lab, we're going to compare the measured results with the results from analysis or from your calculations. We also want to reduce the parallel circuit into an equivalent circuit with just one load. So of course we'll just discuss that again. It was discussed in the class. How do you reduce the number of resistors in a combination circuit to simplify the circuit? We will then calculate and measure the voltage across each resistor and the current in each branch. And of course, we'll discuss the voltage divider rule and the current divider rule. So for this lab, this is the equipment that you need. We have a power supply, breadboard, and some resistors. So we have 100 ohm, 330 ohm, 1K, and 10K resistors. Now, why is this important? Because in general, most circuits that we see are combination circuits. They have parallel components and series components. And of course, we need to know how to work on those circuits, how to analyze them. So this is why we are doing this lab. When two or more components are connected in series, all the characteristics of a series circuit apply. And when two components are connected in parallel, all the laws or characteristics of a parallel circuit apply. So anything connected in parallel, for example, we said if you have components in parallel, the voltage is the same across them, and that is the same thing you're going to see as we continue in this lab. Also in parallel, we know that the current splits up and it goes through the different branches based on their resistances, and that will also apply. So you see on your screen here a series circuit by itself. It has one path of current to flow, and the voltage across each component is going to add up to the voltage across the source. And this one here, you see a parallel circuit. Of course, we have current flowing in each branch, and that current adds up to make our total current, and the voltage across each component is the same because they are connected in parallel. So how do we reduce a circuit to find the equivalent resistance? To find the equivalent resistance of a series parallel circuit, you must combine all the series elements to find the equivalent resistance for the series portion, and also you will combine the parallel circuit elements. So again, you want to simplify the circuit. You want to identify, okay, which two components are in series that I can combine, or which two components are in parallel that I can combine, and you continue that way. And we have some examples here to help you out. So here is our circuit that we're looking at today. You can see here we have a circuit with these two components here are in series, and they're in parallel with this one, and of course in series with that one. So again, how do you solve this? What steps are you going to take? So of course we can see all the steps apply here. So total current comes from the source, it passes through R1, so we know the current going through R1, and that current is going to split up. Some goes through IA and the rest go through IB. Of course, based on parallel circuits, we know that the smallest resistor, the branch with the smallest resistance, will have the most current. And we also know that because these two branches are in parallel, they have the same voltage across them. That is what we mean by applying the characteristics of series and parallel to the circuit. So again, how do you measure how do we simplify the circuit? So again, we can see here that these two resistors are in series, so we can obtain the series resistance by adding them. So you can see that R34 is going to be R3 plus R4, and so we replace R34 with one resistor, which is R34 here. And you can see that, okay, these are in parallel. So okay, how do you find parallel resistance? You can use this method where you find the conductance, and then you say 1 over the conductance will give you the resistance. So this is to find the conductance. So if you take 1 over the conductance, you will get the resistance of these two parallel resistors. Another way to do it is to do the product over the sum, where you multiply this one by this one divided by the sum of the two of them. That also gives you the parallel equivalent resistance. So after we simplify this and we find the total parallel resistance, we have R234. and you can now see that our 234 is in series with our 100 ohm resistor, and then we can then find the total resistance of the circuit. We can reduce this into one resistance. So you can see when we add R1 with our 234, we have Req, or R equivalent, and this will be the total resistance of our circuit. Okay, here we have another example here. Let's look at this example quickly. So this is figure 5.4. We have a series parallel branch, and of course, first step is to identify things that we want to simplify, and of course we can simplify here. We have a series branch here. So you can see here that we can find our 5/6 by adding our 5 and our 6. Then it's going to be in parallel with this branch with our 4 here. So the resistance is going to be, we can do product over sum for our 4 times our 5/6 over our 4 plus our 5/6. Another way to do it is to do it using the conductance method shown here. So the resistance is going to be 1 over our 4 plus 1 over our 5/6. Then after we find the parallel resistance, we can see that it's going to be in series with this resistor. So then we have our 3 plus our 4/5/6. So then after we solve this, so we have a series resistor here. It's going to be in parallel with this. So of course we find the parallel resistance, R2, in parallel with our 3, 4, 5, 6. And after we resolve this into one resistor, it's going to be in series with R1. So that will be our equivalent resistance, R1 plus R2, 3, 4, 5, 6. So it's a good example for you guys to work on and to try to get the correct answer. What is a voltage divider? A voltage divider states that in a series circuit, the ratio of the voltage drops across the resistance is the same as the ratio of the resistance values. And I've been mentioning that to you. So again, in a series circuit, we said the voltage is dropped across the different components or the different elements in the circuit. And how do we know how much voltage is dropped across which resistor? Well, that is based on the resistance of the resistor. Actually, the ratio is actually the same. So the ratio of the voltage of that resistor to the total resistance of the circuit is the ratio of the voltage that will be dropped across it based on the supply. So what does that mean? It means that if you have equivalent, if you want to find the voltage across R2, it's going to be the ratio of R2 over the total resistance. That gives you the voltage across R2. All right, so again, the ratio of the resistance of R2 over the total resistance of the series circuit is the same ratio of the voltage across R2 to the total voltage. So how do we implement this voltage divider? Now, of course, you can see here, most times it looks like this. So sometimes we say that we use a voltage divider to give us a particular voltage, and it will be the voltage across this resistor right here. So to find the voltage across R2, we simply say R2 divided by R2 plus R1 times the voltage source, and you will know what fraction or what ratio of the voltage is across R2. And if our output is connected here, of course, the voltage across R2 will be the voltage across our output. So again, this is very important. You can use this equation to calculate VR2. You can also use it to calculate VR1 as well. Of course, you will change R2 here to R1. Now we can also discuss the current divider. So again, when we have a parallel circuit, we know that the current is going to split between the two different branches. And so what we do is that the amount of current is going to be based on the conductance that is in each branch. Now, conductance is 1 over resistance. So what that tells us is that the smaller the resistor on the branch, the larger the current in that branch. And so what we do here is we simply we're saying that the ratio of the current in each branch is based on the ratio of the conductance in each branch. And of course, we know conductance is 1 over resistance. And so it's for the current divider equation. If you have two branches like that, if you want to find the current in this branch, you're going to use the resistance of the other branch divided by the resistance in the branch you want to find and the other branch, and you multiply that by the current. So again, the ratio of the current in each branch is based on the ratio of the resistance in the other branch over the sum of the resistance here. And we call that the current divider equation, sorry. So let me just change this. This should be a current divider. Okay, let's continue here. So again, this is your procedure. Very simple. Using the problem solving method that have been discussed, and of course is discussed in your lecture, do the following. Calculate the total current, total resistance, current in branch A, current in branch B, VR1, the voltage across each resistor. And of course, you're told to use the current divide and voltage divide equations where appropriate, and of course, record your results in R2. So this is your resistor, this is your table R2. You can see the table here has a section for all of your analysis results. The second part of the procedure says, measure the actual values of your individual resistors. So you need your 4 resistors, a 100, a 350, 1K, 10K. And it says then, connect your circuit as shown in figure 5.2. Notice that the resistors are 3 and 4 in series. And R3, 4 and R2 have the same ends connected directly and they're in parallel. Measure all the voltage drops across each resistor. Also measure the voltage across R3, 4. Then measure the total current and the current in each branch and record your results in the table. Then of course, complete and submit the lab report. Alright, so we're going to do some analysis for this problem very quickly. Again, this is the combination series parallel circuit. So again, let me just draw the power supply. And so we have a resistor here, we have another one here, and we have another one here, we have another one here. Alright, so again, R1, R2, R3, R4. Looking at this circuit, we can see that we have a relationship here between these two. These two are in series. So if we were to solve this, first we can say, okay, we can say that R34 is equal to R3 plus R4 because they are in series, right? Then we can see that this resistor, if we replace it with 1, is in parallel of R2. And so we can say that R234 is equal to R2 in parallel of R34. And we can solve this very easily using the product over the sum. So it's going to be R2 times R34 over R2 plus R34. Then we have this one in series here. So after we replace all of this with one resistor called R234, it's going to be in series with R1. So we can say that our RT now is equal to R1 plus R234. Right, so this is how we will find the total resistance for this circuit right here. So an easy way to do this, let's put some values now. So I'm not going to use the values we use in the lab. I'm just going to use some different values so that you can get a chance to do the one in the lab. So I just change one value. Instead of 330, I'm going to use 470. Alright, so of course in your lab you use 330. So how do you find the total resistance here? Easily you can see this. If you can visualize this, you can say that, okay, the total resistance is going to be R1 in series, so we put a plus, with what? With a parallel branch, a parallel of what? With R2 in parallel with what? Parallel with R3 and R4. R3 plus R4. So you can easily see this, that, okay, this is going to be in parallel with this, and so you can solve this as well. So the answer is going to be 120 plus, and of course for this we're going to use the product over the sum, so the product is going to be R2 470 times, and of course we can compute the sum even in our minds. 10k and 1k is 11k times 11k over 470 1000. Okay, hold on, that will be 1570. If you add 11,000 and 470, we're going to have 11,000. Okay, hold on, errors here. We're going to have 11,470. Right? And so when we solve this, we're going to have, if we calculate this, let me just get my calculator. We're going to have here 470 times 11,000. 470 times 11,000 divided by 11470, and the answer will be less than 470, so we can see that the answer is 450. So all of this adds up to 450, and then we add it to 120. What do we get? So 450 plus 7.7 plus 150, 120. Okay, we have 570 as our 0.7 ohms as our total resistance. Now keep in mind that this is not the same circuit in our lab, it's the same configuration. I just changed some values. So I changed this one from 100 to 120, I changed this one from 330 to 470. just so that we can go through the analysis. Okay, so first thing you find is you find the total resistance, and that allows you to find your total current in your circuit. So quickly, our total current is going to be equal to IT is going to be equal to, according to Ohm's law, Vs, of course Vs is our 5 volts, over RT, which gives us 5 volts over 570.7. That gives us 5 divided by 570.7. It gives us 8.76 milliamps. 8.76 milliamps. So this is our total current that is coming from our battery here. This is our IT, total current. Now this current is going to split up here and here, so we need to figure out how it's going to split up. So this is why we're going to use the current divider equation. So for the current divider equation, we are saying that the ratio of the current is not based on the ratio of the resistance in the branch, but the ratio of the conductance. And the conductance is actually 1 over the resistance. So that means the branch with the smallest current, the branch with the smallest resistor will have the most current. And so the way you set up the equation is very similar to the voltage divider equation, but you use the opposite resistance. So for example, if we want to use the current flowing through this branch, we're going to put the resistances here over the total resistance times the total current coming in. So that tells us how the current is divided. So again here, so if you want to find IA is going to be equal to R34 over R2 plus R34 times the total current coming in IT, which gives us 11K over 11K plus 470, which is 11,470 ohms, times 8.6 milliamps. And that gives us, so the fraction is 11 divided by 11.470, and that's 0.959, and we multiply that by 0.00876 amperes, and so that gives us, you can see that most of the current is flowing through this branch here. So the answer is 8.4 milliamps. So knowing that, we can actually know what IB is. We can decide to calculate it using the current divider equation, where instead of putting R34, we're going to actually put R2. Or we can just use Kirchhoff's current law. Since we know that these two currents add up to make this one, and we know this one already, and we just found this one, we can simply subtract. We can say that IB is IT minus IA, which gives us 8.76 milliamps minus 8.4 milliamps, which is going to be equal to 0.36 milliamps, right? So we found all the currents. Now to find the voltages, it's very easy. We can use Ohm's law, and since we know the current going there and we know the resistance, we can simply multiply and find the voltage. For example, VR1, we know the current going through this resistor is going to be the total current, and this is where it's going to split up here. So this is going to be IT times R1, which is going to be 8.76 milliamps times 120 ohms. So again, calculate it here. 876 times 120. So the volts is again 1.05 volts. So this is the voltage that is dropped across this resistor here, and the rest of course is going to be dropped across here. So of course, if you find this one, then we know we started with 5 volts, and then we have we dropped 1.05. Of course, the rest we have left is going to be 3.95. It's going to be across this resistor right here. And of course, since this is in parallel fit, it's going to be across this branch as well. So VR2 is going to be equal to, we can say, Vs minus VR1 based on the configuration of the circuit. So that gives us 5 minus 1.05, which is going to be equal to 3.95 volts. All right, so this is one way you can find it. Again, that's based on the configuration of the circuit.
We can also very easily calculate it. So we know the current going here. We can also say that it's going to be IA, that's the current there, IA times R2, which is going to give us 8.4 milliamps times 470. So I can calculate it here. 8.48, that's 8.4 milliamps is the same thing as 0.0084 amperes times 470. And you can see we have 3.948, very close to 3.95 volts that we calculated here, right? So it's very similar. In this section here, we know the voltage across these two resistors is going to be 3.95, and so some voltage will be dropped across here, and the rest is going to be dropped across here. To find that voltage, we can use the voltage divider equation, and again, this is how we do it. We say V R3 is going to be R3. Again, for voltage divider, you always use this. We have here, we can look at this equation to find our total resistance, and we can see that these two are in series, so of course the total resistance is going to be R3 plus R4, and we can see that this, if we replace it with one resistor, is in parallel with R2, and so we can see that that's what this represents. To solve that, we can use the product over the sum to solve it quickly, and then the total resistance is going to be R1 plus whatever the equivalent is from the parallel result. So this is what we have here. Of course, the values in this are changed, so it's not the same as your lab. So you can go ahead and practice the one for your lab. So again, we have 120 plus 470 times 11K over 11K and 470. And of course, the total resistance is 450 for this parallel set here. So when we add it to 120, we have 570 ohms being the total resistance of the circuit. Using that, we can find the total current in the circuit, which is going to be V, the total Vs over RT. 5 over this gives us 8.76 milliamps. So this is the total current coming from our battery. Now we know the current is going to split up here. So IA is the current here, and of course IB is going to be the current that flows here. Now just looking at these resistors, we know that the current is going to, more current is going to go in the smallest resistor. So this is 11K, very small current will pass there. So again, here we use the current divider equation. Now we say with the current divider, since we want to find IA here, we put the resistances on this branch, in the opposite branch. So you can see here we want to find IA, which is the current here, and we put the resistors in the opposite branch. So R34 over R2 plus R34, and so that gives us 11K over 11K 470 times the total current that we have that we need to split, and of course we get 8.4 milliamps. So majority of the current passes through IA. Now to find IB, we can do the same thing, and instead of R34 we can have R2, but we decided to subtract since we know that IA and IB add up to make IT. We can say that IB is IT minus IA, so we get 0.36 milliamps for IB. Next, we wanted to find the voltage in resistor 1, so we used Ohm's law. We said, is the current flowing through that resistor times the resistance? So the total current is flowing through that resistor, so we have here 8.76 milliamps times 120 ohms, and we get 1.05 volts. For VR2, since we know that essentially these two voltages are going to add up to 5 volts. Again, the voltage across here is in parallel, it doesn't affect this. Then we can simply say 5 minus the voltage here will give us the voltage across this resistor right here. And that's what we did here. We said here 5 minus 1.05 is 3.95. If you wanted to calculate it the same way we did this one, we can do it as well. It's going to be IA, which is the current flowing through that resistor, times the resistance R2. So you have 8.4 milliamps times 470, and it will give you very close to 3.95. Thirdly, we wanted to find the resistance going through R3. Now again, we can use the same method to find it, where you can say, okay, well, what is the current going through I3? That current is IB, so you can say it's going to be equal to IB times the resistance here, or 1K, right? And so you can calculate the voltage as well. So again, our IB is like 0.36 milliamps times 1K, right? So it's going to be equal to let's say 1, 2, 3. So it's going to be equal to like 0.36 volts, right? That's what it would be if we calculate it using this method, but we decided to use the voltage divider method, where you have to put the resistance. If you want the voltage across R3, we have R3 over R3 plus R4, which are the series resistors, and of course multiplied by the voltage that we want to divide, and that voltage is 3.95, so we get 3.59. So it's very close to this. So again, this is another method to do it. Now we can also calculate the voltage on resistor R4, but we said since we know that resistor R3 and 4 add up to 3.95, we can simply subtract. We can say, okay, 3.95 minus our VR3, and we will get what is left. And of course, we see that VR4 is much larger than VR3. That is because the resistance is much larger than the resistance of R3. A ohm meter that is going to measure the total resistance of this circuit. Again, this is the series parallel circuit. You can see that this 100 ohm resistor is in series and these two branches are in parallel. But however, this branch has two resistors, so these two are going to be in series. And when we connect our power supply to it, we're going to have here our 5 volts coming in here, and it's going to come into the 100 ohm resistor, and the negative is going to go to the junction between the 330 and the 10k resistor. So this is the circuit that we're referring to in our procedure. Again, for our procedure, we have two sets of steps. The first step is the analysis. This is where you are told to find the unknowns in the circuit by using the equations that are given in this lab. So it says, using the problem solving method, solve the circuit in figure 2 for the following. Find the total resistance, total current, the current in branch A, current in branch B, voltage across resistor 1, voltage across resistor 2, voltage across resistor 3, and also the voltage across resistor 4. And you are encouraged to use the voltage divider equations or the current divider equations where appropriate. The next part of our procedure is to measure the actual resistor values, then connect the circuit as shown, measure the total resistance of the circuit, then connect the voltage, and then measure the total voltage, measure the voltage across each resistor, measure the voltage across the branches as well, and also measure the current, the total current, and the current in branch A and the branch current in branch B. And then the last step, to complete and submit the lab report. Very important. So again, I went ahead and drew the circuit on here. So you can see this is the circuit that we're going to build, and we're going to measure the resistance from the point of the first resistor to the junction right here, and then we're going to build the circuit. So I just want to put some labels on here. So again, this is resistor 1, 2, 3, 4. Also, we are told to find the total current. That is the total current that is coming from the battery, and we will call this IT. See if you have another color marker here. So this is IT, the total current that is coming from the battery. Now, of course, according to Kirchhoff's current law, we said that this current is going to split up. Some current will go in this resistor and the rest will go in this branch. And of course, just looking at the resistances here, this is 330 and this is going to be 11k when we add the 10 with 1. So we know that most of the current will go here, so we call this IA. And we know some current is going to go here, not as much. We'll call this one IB. And of course, we want to measure those. We can calculate them, we can also measure them. So the first step is to build a circuit. So again, here are the resistors. We have the 100 ohm resistor here. This is R1. Then we have the 330 ohm resistor. Now yours may not look like this. I just couldn't find mine, so that's why I'm using this. This is the 1k here, and this is the 10k. So I'm going to go ahead and measure them. Now the lab instructions tell you to put all your results in the table, and so let me show you what the table looks like. This is on page this is going to be on page number 7 in your report. So on page 7 here you have a table where you can measure let's just wait so we can focus. There you go. We have a table where we can write down the measurements for the resistors, and then we have a table where we can write down our results for analysis and our measurement results. So for the purpose of this lab, I'm just going to write them on this sheet of paper as we go, right? So I'm going to start by just putting an area where I can write down my measurements. So again, R1, 100, R2, 330, R3 is 1k, and R4 is 10k. So I'm gonna write down the measured values for each of them. So So again, to measure resistance, your meter should be on the ohm symbol here, and your probe should be in the volt ohm probe, in the volt ohm port. So I'm going to move it here quickly, and now I can measure this resistance. So again, you can do it this way. The easier way is to put it in the breadboard and to measure it. Since the resistance are pretty small, I'm just going to hold them like this. It shouldn't interfere with the measurements at all, because the measurement of the human board is very large. 100.2, 100.4 ohms. So I'll write that down here. So it's pretty accurate. The next one, 330. So I'm holding it here. 327.0. 327.0. The third measurement is here. Again, this is our 100 ohm resistor. Sorry, 1k ohm resistor. It's exactly 1k. 1 kilo ohm. And our 10 ohm resistor. So I'm holding it like this. Again, just bring it closer so you can see. Maybe it'll focus on my hand. So for the 10 ohm resistor, we have 9.82k. 9.82k. Okay, the next step, we're ready to get started in building the circuit, right? So again, if you look at the circuit here, it tells us what we connect to what. So again, I have my breadboard here. I already have, so I'm gonna put this guy here and this guy here. So I already have the orange connected to 5V here, which will supply my positive 5 volts, and then the white side is connected to ground. All right, so the 100 ohm resistor is connected to my positive, and so what I do, I will just take this and connect it to my positive. Again, just putting it in the same row with this here. So I'm gonna put it right here. So I have now connected this part of my circuit. 100 ohm is in the same row with this guy right here, and so this is how it's connected. So I have now connected this portion. So now you can see that I need to connect this resistor right here as well, or rather this 330 ohm resistor. One leg is connected to the 100 ohm and the other leg is connected to negative. So again, this is the other leg of the 100 ohm. I will put the 340 ohm in this hole right here, and I'm going to bring the other one across for the 330 ohm resistor. And you can see that the other leg of the 330 ohm resistor is connected to ground or negative. So I'll just move the negative into the same row with that resistor so that they can now be connected. Yeah. The next step is with the 1K resistor. They are connected in series across the 340 ohm resistor, and so I'll take the 1K ohm resistor and I'm going to put it in the same row here so that it can be connected to the 340 ohm resistor. Now I'll just put it right here, and the 10K ohm resistor now you can see is connected in series with this one, so it needs to be connected to the 1K. So I put it in the same row here, it's connected, and you can see now the other end of the 1K ohm resistor is connected to the junction. So I need to, and that junction is connected to negative, so I need to connect the end of this resistor to the junction here, and so I just need to put it in the row right here. Okay, then we continue across the second resistor, which is the 330 ohm resistor. The voltage is 3.74. Then across R3, voltage is 0.34 volts. Lastly, then across the last resistor, which is the largest resistor, we have 3.38 volts. And that makes sense. Why? Let's tell you why this makes sense. Because if you notice here, the total resistance of this is going to be equal to 300 and something volts. So we expect that most of the voltage will be across R2. Then the same voltage is divided into 2 based on these 2 resistors, and of course the resistor with the most resistance will have more of the voltage across it. That is why VR3 is so small and VR4 is so large. The second step now is to measure the current going here. Like I said, the branch with the smallest resistance will have the most current, so of course we expect most current to be on IA. Let's go ahead and measure current. Now to measure current, we said we need to change the meter to milliamps, and then on your meter you need to find the milliamp port. So make sure that the meter is in the right port. Okay, that's the wrong one. So we need to be in the milliamp port, and of course on the meter we are set to measure milliamps. And so now what we do, the circuit is still connected. What we're going to do, we're going to separate the circuit and use the meter as a jumper so that the current can go through the meter. So I'm going to disconnect this positive going into the first resistor. I'm going to put it somewhere else on the breadboard. And then I use my meter that is connected as a ammeter, and I took my 2 probes and I connect them between the gap that I just created. So the meter acts like a jumper. So you can see here that the total current being measured is 11.99 milliamps, very close to 12. So I'm going to write it down, 11.99 milliamps. Secondly, then I need to, so I'm going to put this back, connect it back. The second step now, I need to disconnect this. I need to disconnect this and use the meter as a jumper. So how do I do that? Let me disconnect the tail end. So I'm going to remove this resistor right here and put it right there. Right, so I just disconnected this one here. Disconnected it, and now the meter is still connected to measure current, and now I'm going to use the meter as a jumper to go between this resistor now and ground. And so you can see the current flowing here is 11.68 milliamps, 11.68 milliamps. So IA is the majority of the current. IA is 11.68 milliamps. Most of the current is going through this resistor right here. So I'm going to put it back. Of course, you can feel free to turn off the circuit before you work on it for safety reasons. And lastly, I'm going to disconnect this branch here. So I'm going to measure the current actually flowing in between these two. Now it doesn't matter if I measure it here or at the end, but I'm just going to do it in the center here. So to do that, we simply move the 10K resistor, put it somewhere else. So I'm going to put this somewhere else, and now I'm going to use my meter as a jumper and go in between the two of them here. Let's see if we are focused correctly. So again, the meter is jumping. The meter is now connecting the 2 points, and you can see that the current on the screen is 0.35 milliamps. So I'll make a note of that. And that's it, we're done with the measurements.